pain in the ass because you lose a lot of your peripherals with these. So I find myself talking to people, I gotta go, what? Like, I gotta go all the way around.
That's okay. That's okay. Batman does that too. Michael Keaton, right? What? Yeah, it depends on your prescription. Yeah, I think my worst eye is only 2.5 diopters, so it's not really that bad. If I take off my glasses, I can still read the screen at about maybe foot and a half, 18 inches or so. So it's not quite that bad. I can still drive, marginally. Oh, -5. Yeah, yeah. So you guys need the extra thin, high. They call it high refractive index, plastic. My polycarb is almost bulletproof. Almost. Yeah, yeah. Polycarb is interesting. Because I shoot pellet guns as a sport. There are competitions. So if you shoot polycarb or plex not yeah, is it the same as plexiglass? Yeah, but anyway, if you shoot polycarb with a pellet gun, it doesn't crack. It deforms. It's almost like it's semi-metallic. It just deforms, makes a dent. Yep. Uh, hmm? Yeah. Yep. All right. So we are. Do you guys want me to go over the lab from last Wednesday? Which is the 3x3, part A, part one. Yes. Okay. All right. We can do that. All right. So I'm just going to reproduce, the lab, and I will recall as much as I can, just from memory. So I think we have three input pins where the positioning of the three input pins is significant. So you have to make sure the X is on the left hand side at the top, and then once I have X, I can replicate it for Y. Hmm? Oh, okay. So here's Y. That's okay. I don't think I took all the points off. If you misplace it, but you do get some points deducted if it doesn't work in the tester. All right, so K0 is the one that only has one single bit. So those are the input pins. The input pins, output pins are not really designated yet, because it's you need the carry bits in order to work out the output pins. So these are the three input pins, and then I used tunnels. And tunnels are really useful when you have a more complex circuit. This one is not even close to complex, so I'm not going to be, you know, it's not 100% necessary to use tunnels in this case. But when you have a complex circuit, the use of tunnels can really help to make the circuit easier to read because um, every tunnel with the same name, but it's case sensitive, are basically logically the same node. In other words, they connect to the same conductor or conductors um, in a real circuit. So they're pretty handy, to make a circuit look nicer when we're looking at just the schematic. So schematic is a special term to refer to the logical connection between the components. So in other words, I cannot really make a circuit board out of, these diagrams because we have wires that are flying all over the place. So in order to change a schematic into a circuit board layout, you need one extra step in between, which is called routing a circuit board. Obviously, I'm not going to teach you guys how to route a circuit board, but it's interesting. It's kind of fun. It's kind of like solving puzzles, except in this case you have a two-dimensional plane, and you need to find out how to route the wires from one point to another point without crossing over when they're not supposed to cross over. All right, so we got X, Y, and K0, and then we got a few gates, right? So we got an AND gate, we got an OR gate, and we also got an exclusive OR gate, like so. And then on one side we have the three tunnels. So I'm going to do the really lazy thing here, which is to copy or duplicate these. And then I will go ahead and flip their direction all at the same time. So you can actually change their facing together. So this way, they're all flipped to the other side. And then with all these, I can change all of their appearance and also change all of their number of input pins and also their number of data bits, at the same time. So it's just, a nice, time saver if you learn how to use LogicSim by batch changing your components. All right, so we got these three, may not be in the same order as in the lab. And then we got 3 additional tunnels, which are supposed to be the outputs of these gates. So we'll duplicate this and then we'll change the names. So on this side, we're going to flip the direction again back to west, and then we'll change the names. One is P, and in the question, I use uppercase P, so I'll just stay consistent with that. And then we have uppercase G, and then we also have uppercase Q. May not be in the same order, but this ordering is not as important as the pins. All right, so that's kind of how we started with this particular lab. Is I gave you a picture, and you're supposed to wire things up, as they are defined in the binary addition module. So the first thing we need to do is to find the definitions. So that's why I have been trying to ask you guys to take notes and to copy all the definitions to one single spot so it's easy to define. In other words, we need to find out what is a P, how is P defined, how is G defined, and how is Q defined in terms of X and Y, and possibly K0. And I'm not giving you any clue in the lab because this is supposed to be a review of the material just to see whether you guys are familiar with the definitions or not. So are we good so far? All right. So I'll just go really kind of quick here. Okay, so P is the OR between X and Y. So, the output of OR, which is red right now because it doesn't have any actual input, so the output cannot be determined. That's why it is red for now. G is from an AND. And then Q is from the exclusive OR. So in this particular case, they are arranged like this. And then they're all, basically using X and Y to do all the computation. So X is going to, quote unquote, multi-drop into one of the inputs of the gates. And then Y is going to do the same thing. It's going to the other input of the gates that we already have in this diagram, like so. All right. So this part, relies solely on, whether you understand the definitions of, how is PI defined. PI is defined to be XI or YI. GI is defined to be XI and YI. And then QI is defined to be R of XI, YI, but that is also known as XI exclusive OR with YI. So anyone who is kind of struggling with this lab on last Wednesday probably need to do some more review of the material, and also try to focus on the definitions, because right now we are not doing any reasoning. This is all coming straight from the definitions. So once we have this, then I asked, in the lab instruction, we need to construct K1, K2, and K3. So this is how we construct K1. So K1 has 3 input pins. Once again, the ordering and the positioning of the input pins is significant. So I need to make sure that I use the same kind of ordering and the same relative positioning as what the lab is indicating. So the last one is going to be my K0. And then we have P and Q up here. So this is another circuit. So these pins, even though they're named P and Q, or P and G, so even though they are named P and G, just like P and G in the main circuit, they are in no way related to anything in the main circuit. Okay, this is its own subcircuit, and there's no relationship between this circuit at this point with the main circuit whatsoever. On the other end, we have an output pin, which is a K1 in this case. So I think one person did not use any output pins whatsoever. So the grader or the test driver basically say, hey, where's the output? I cannot check, when there's no actual output. So that, that person got, some points deducted because of that. I'm not sure whether it's from this class, but one person was using an output pin, excuse me, an input pin instead of an output pin for K1, which resulted in E because, an input pin, can change a wire, the state of a wire, but an output pin is only here to reflect the state of a wire. All right, so at this point, we need to go back to the notes because I am really poor in terms of remembering things. So I have to go back to the notes, go back to binary addition, and I need to find out the carry lookahead equation for K1. K1 is easy. It is just G0 or P0 and K0. So once again, these are not arithmetic operations. I simply borrowed the notation, but in this case, they are representing Boolean operations. So going back to here, we need to grab an AND gate. We need to grab an OR gate, and they're way too big, too many inputs, so we need to change the number of inputs to 2 in this case. Scroll up, there we go, change the shape a little bit, there we go. All right, so I think G0 is on its own, it goes straight to the OR gate, but when you look at this G here and this P here, they are not correct because they're supposed to be 3-bit wide. So now, when you look at this particular wire, it is 3-bit wide. Now, how do we know it's 3-bit wide? If you just change to the poking tool and just touch it, you will see that it has 3 bits, okay, which is not okay because the equation that we need to use is referring to just G0 in this case, which is a single bit. So what we need to do is to use a splitter to split the input pins, P and G, into the 3 individual bits so that we can utilize the individual bits. So now we go to wiring, we go to splitter, and we need the width to be 3-bit wide. But I'm just going to use a fan out of 3, even though 2 are not going to be used. It doesn't matter, okay? Because even if you leave 2 of these unused, the circuit is not incorrect, which means we can just go ahead and do it this way. So we need 2 splitters like that to split P and G into P0, P1, P2, and then G0, G1, and G2. So now we have all the individual bits that we need. G0 needs to go to the OR gate all by itself. So just to make the diagram look a little nicer, I'm moving things around just a little bit, just so that okay, needs to go up 1 more notch. There we go. There we go. Okay, so now we have G0 connected to the OR, but we also need K0 to be ANDed with P0. So I'm just playing with the layout here a little bit, just so that it looks somewhat nice. Okay, there we go. And then the output of the AND is going to the second input of the OR. And now the output of the OR becomes the actual output. So I'm just gonna line things up a little bit, because this way it looks a little nicer. There we go. And we have an issue because somehow Logisim thinks this wire is undetermined when it is supposed to be determined. All right. So this is a bug of Logisim. I have no idea how to reproduce the bug. So when something like this happens, if you suspect it's a bug of Logisim, save the file. So I'm just going to save the file to, let's see. I just save it in the home folder. We'll call this 3x3ca. So quit Logisim, or you can say, open, and open the same file. Maybe that'll work. We'll see. All right, so we open the same file, and now it's okay. So Logisim has a bug. I do not have the time to debug it yet, especially when I cannot easily reproduce the problem. But this time I may be able to do it because normally I do not have screen recording turned on when I work with Logisim. I do have everything being streamed to YouTube right now. Let me just double check and make sure that is the case. Pretty sure. Yeah, there we go. So I can actually go back and reproduce exactly the same steps. So unless it is a timing issue, which is unlikely because LogiSim does not have any actual timing components to it, I think I can reproduce this bug and potentially fix at least one of these bugs. So this is K1. And then once we have K1 done, I go to the appearance, the circuit appearance of K1. This part is not really needed, but I would do it anyway, because I want to know, which is P, which is Q, what is K0 as the inputs. And then in this case, the output is K1. So this way, I won't mistake this circuit for something else. So we have, oh, that's not supposed to be Q, it's supposed to be G. Alrighty, so go back to the text tool. It does allow you to change the text of a previous label. So this is G, and then we got K0. And then the output is K1. So they all kind of fit nicely within the rectangle. All right, so we got K1 done. Now it's time to work on K2. Go to Project, Add Circuit. This is K2. And since I got K1 already done, I'm going to copy and paste. Even though the gates, are not going to work out the same way, at least the input pin and the output pin would work out too. So I'm going to just copy this, paste it here, and then just remove all the wiring in between the input and the output pins. So this way, I can at least have a template to start with. All right, so now we go back to the notes because I cannot remember what K2 looks like. This is K2. So K2 requires G1, P1, G0, P1, P0, K0. So this time I'm going to use a trick in this system. I'm going to take a screenshot of just the portion that I need, like that. And then I open it with a particular program called Fed, which is just it opens up a graphics file and let you view it. So by itself, it's no big deal, nothing really too fancy about it. But what I can do here is I can now, once I find it over here, I can make it always on top. So, all right, it is always on top, supposedly. And then I can just move it here. So when I construct the circuit in LogiSim, I can keep an eye on the actual circuit. Yes, my memory is that poor. I cannot remember something as simple as this. So by the time we get to K3, I definitely need something like this to remind me how to construct it. So according to this, we need two AND gates because one AND gate is going to compute the conjunction of P1, P0, K0, the other AND gate to compute P1, G0. And then we need one final OR gate to take G1, the output of one AND gate, and then the output of the other AND gate, and OR all of those lines together. All right, so let's go ahead and get started with the gates. So we have two AND gates and one OR gate. There we go. And once again, they're way too big, for what I. Uh-oh, my computer just froze up a little bit. There we go. And then we turn them into the smaller form. Change the number of inputs to 3 this time because I know 1 is supposed to be 2, but the other 2 are supposed to be 3. So we'll change this one to 2. So now we got all the gates. And then the OR gate is always going to be the last thing that we need before we get to the output pin. And of course, the output pin is no longer K1. It is now K2. It's good to change the name of the output pin so it reflects what it's supposed to be. All right, so in terms of the diagram, we need G1 to go to one of the OR gate pins. So here's G1, and we'll just draw a line right there. Now we also need P1G0, and that's the one that needs the 2 input AND gate. So since it doesn't need K0, so I'm going to put it up here, and I'm just going to make it align with P1. like so. So P1 goes here, and then G0 goes to the other input pin. And then the last one is P1, P0, K0. So that is the one that requires the AND gate that has 3 inputs. I'm just aligning things so that they end up looking nice. So here's one. We need both P1 and P0 in this case. All right, so we'll put this one. Oh, that's not gonna look nice, but it will still work. Alrighty, so we'll wire this one up like that. And now we have to send all the outputs of the AND gates to one of the inputs of the OR gate, like so. And now we got K2. Any questions about K2? No questions? All right, then we just need to work on K3. So once again, copy, and then go to Project, Add Circuit, K3, and then paste. All right, so I'm gonna once again remove all the wiring, but this time I think I'm gonna keep the gates around just a little bit longer. So there we go, we get rid of all the wiring. And then we need one more AND gate in this case because we need one of the AND gate to have 4 inputs because this is no longer reflecting what I'm working on. This time we're working on K3, which looks like this. So I'm going to use the same trick. Capture just a portion of the screen, display that using this tool, and then change it so that it displays always on top. And now I can move it around to a spot where it's not going to interfere with LogicSim, and then continue to work on LogicSim here. All right, so this time we need one more AND gate that has 4 inputs. So I'm going to take this one, just duplicate it, and have this one to have 4 inputs, like so. G2 is feeding directly into the OR gate, so it's this guy here. Oh, the OR gate also has 4 inputs this time, so I got to change that one too. So it's 4 inputs. There we go. And the one that requires K0 is the 4 input one, so I'm going to put that one all the way down here just because K0 is already down here. And let's see, like that. There we go. So now we got K0. And then we also want all the P, P0, P1, and P2 to feed into the other 3 inputs of this AND gate. So this time I'll try to see if I can make it look kind of nicer. Here's 1. And here is 2. And here's 3. There we go. All right, so this AND gate is done. Now we work on the AND gate that has 3 inputs. And it's going to be this one. This one needs G0 and also P1, P2. So P1 is right here. So P1 is, I can just tap it from here. And then P2 is right here. There we go. Doesn't look too bad. And then the one that has 2 inputs requires G1 and P2. So this one, okay, I can still make it work. It's just, gonna be a little bit more ugly. All right, so we'll take care of the P2 first. This is P2. And to get that without interfering, crossing with any other wires, I kind of have to do it like this. And then G1 goes to the other input pin, which is all the way up here. And that one is not too bad, just like that. And now the output of every single input pin goes to, the output of each AND gate goes to one input of the OR gate. Oh, that was not intended. And now we have K3. All right, so I need to test whether this works or not. So there are a few ways to test this. You can go back to main and test it by placing K1, K2, K3. Oh, I forgot to change the appearance of K1, K2, and K3. So K2 and K3, they do not have a something that's usable. So I'm going to shortcut this a little bit just to make sure that this is K2. And then we'll go to this one and make sure it is noted as K3. Because the inputs are all the same, okay? We got the P, the G, and the K0 at exactly the same position. So it's just the output that is different. And I need to make sure that this one is also, in terms of documentation, this output pin is supposed to be K3 as well. It doesn't really matter, because, it's not really, that there's no implication if I name the pin incorrectly, but it's still nice to have it named correctly. All right, so now we got main, we have K1, right? We got K2, we got K3. And then what we'll do is we're going to feed the P, G, and the Q into these things. Well, just the P and the G, and then also K0. So this is P. So P is going to multi-drop, into this. You can also use a tunnel, okay? Doesn't matter whether you use a tunnel or just use wires in this case. So here's P, and there is G here. Also the same thing. This is what I would call a multi-drop topology, which is a way of connecting items within a diagram. And then K0 is just going to go to the third input for all three of them, like so. All right. So there are a few ways to test the design. One way is to exercise the input pins like this manually. And then the other one is to use the test circuit thing, to make sure that it does work. So I do want to make sure it works, right? Because I don't want to give you guys something that does not work. So to test that, I need the test driver thing and make sure that this file is saved as 3x3ca. So we'll make sure that it is saved again. And then we have to locate that item. Let me see what I'm going to do here. Okay. I think I know where I put everything. So I'm just going to run the entire command using the really kind of obscure way of running it. I put it into the downloads folder, logicsim310.jar. So this runs logicsim, and then it needs to know what circuit I'm running. And the circuit that I'm running is, I think I put it here. Yep. I don't need that anymore. And then we also need to specify -tty table. Then it's going to run in CLI mode, command line interface mode. Then I want to capture the output to a specific file. I just called it the log file. And then press the enter key. I wonder if what happens in the class if I say that. All right. So it ran without any problem because it for some reason it knew how to find 3x3ca, which is in the current folder. It might not have done it correctly. Let me just double check and make sure. Well, let me take a look at the log file. So what you need to do is to look at the log file and make sure that it is the same as the one given in the assignment or in the lab. So in the lab, let me go find the one in the lab first. Nope, wrong class. I think this may be the right one. Yep. All right, so the one in the lab can be downloaded. Oh, no, this is not the place. It's the previous one. All right, so if you go to the last so-called question, which is not really a question, it is just a description of what you need to do. That's why it's called a spacer. It includes the correct output. So right-click on that one, save it, and then you compare your log file with that one. If your own output is the same, then your circuit is okay. If not, then you might want to double check, to make sure that it is the same. So you change the circuit so that the output is the same as what I'm, downloading here. So I'm going to re-download this, to overwrite this file. So we'll go ahead and do that. Replace. And then using the command line, if you're using DOS, there's a program called FC, or File Compare, if I remember correctly. Is that the name of the tool, FC in Windows? Nobody knows? Okay. In Linux, it's called diff. So I can diff my log file with the one that I just downloaded into CISP310. What is the name again? Test driver ca.log. Oops. 1G. So if diff does not tell me anything, it means the files are the same. So I want to make sure that I am indeed using the right circuit file. So I'm going to remove the one in the folder, or at least rename it. So we'll go ahead and rename the one in that folder, 3x3ca.circ, to something else. We'll call this ca1.circ. And then there's just rerun Logisim again. Okay, so it is the same. So I am using the correct log file, and it is indeed correct. All right. So if you guys did not have a chance, or if you suspect that your circuit is not working 100%, I can share my circuit file that I just created today as a starting point of what you need to do for today's lab. So this way, you don't have to kind of fix your own circuit, if you don't want to, because that can take a little bit of time. So let me do that first, and then we'll continue with the actual lecture content for today. So I'm going to announcement. Oh, this prompts me another question. I have a question regarding this. And the question that I have is, are the announcements reaching your Gmail? Okay. Because I know some people, change to use their personal preferred email. So are those people getting the announcement as email as well?
I think maybe not.
Maybe not. Yeah, you might want to set up an automatic forward. In other words, because I think Canvas is kind of locked to the apps.losrios.edu Gmail unless you set up your own account to use another email. So you might want to double check and make sure, because otherwise the announcements may not be getting to you, which can be problematic. So just a little bit of things that I need to make sure that everything, you can get all the announcements that I make in this class. All right, I think that's it. Nope. Where did I put that file? I did not put it there. All right. Let me double check. Now I have no idea where I actually saved the file, because I know I saved the file. The question is, where did I save it? Oh, in the home folder. That's right. Okay. So let me get out of this one and then rerun everything, because I think I might have been running it in the wrong folder too. Okay. So I'm going to show you something. How do you know, like in this case, which CX3X3CA.circ it is using? So you can do something like this. I know most of you do not want to do something like this, but it is a way to double check things if you want to. All right, so the circuit file is basically what we call an XML file. And in the XML file, there's somewhere here that remembers which the location of the circuit file, and you can see how it is actually in a completely different folder compared to where it's supposed to go. So that means I'm going to have to change that, because otherwise it will be using the wrong file to generate the output. And as a result, whether this particular version of 3x3ca is correct or not, I'm not sure yet. So I'm going to fix that first and then rerun the tool. And then also just do the diff again with, oh, okay, that won't work either. Nope, that should work. Let me just double check. I cannot remember. Okay, so it's saved to my other account folder. Okay, there we go. And then we want to do another diff just to be sure. I'm pretty sure this implementation is correct, but I just want to double check. There we go. Okay, so this one is still good. So let me go back to file upload. And it is not even this account. It is my other account in the root folder. There we go. That's the one that I just worked on. And there we go. So if you check the announcement, now you have the a starting point for today's lab. All right. Any questions up to this point? Nope. All right. So what we'll do today is we're going to work on subtraction because we are basically done with binary addition. So we're going to move on to binary subtraction. And we're going to do exactly the same thing, okay? Except this time it's for binary subtraction, which is I'm going to introduce subtraction, multi-digit subtraction first for base 10. So hopefully everybody in this case, in this classroom, know how to perform multi-digit subtraction in base 10. And then we will extract the structure of just multi-digit subtraction in base 10 using the same kind of notation, the x, the y, the q, and then the other two rows got changed a little bit. And then we'll figure out the relationship between those digits in base 10 in terms of the r, but this time we have a b function for borrow. And then we'll change those functions to work in base 2 to specialize for base 2. And then we'll create the truth table for those things in base 2, and then try to figure out how to perform everything using logic gates. So it's the same journey, except this time it is for subtraction. All right. So with that in mind, let me do one thing. I need to set up the tools to work here. So I need to run this little script here, which is going to fix up the stylus, because otherwise it's not going to work with the program called Zernal. And then we'll go to, you guys would need to see this, and I need to see that on my side. Okay, so I think we are good here. All right, so we're going to work on base 10 subtraction. So I think in my Joplin notes, I actually specified the exact test case. So this is Joplin for today. And then the subtraction is 215 minus 417. So 215, okay, I'm just going to write it down here because otherwise I cannot remember. So it's 215 minus 417, and that's in base 10. So now I can display this again. All right, yes, the horizontal line is not very nice, so we'll go ahead and all right, there we go. I just wanted to look nice. There we go. All right. So the first question is, what exactly is 5 minus 7 in base 10? Now, most of you already know it's supposed to be negative 2 because your 5 is 5. So if you look at the number line, 5 is on this side of the number line, and then you move backwards 7 steps, and it's going to land on the spot that we normally call negative 2. But understanding that 5 minus 7 is negative 2 is not going to help us with multi-digit subtraction. So instead of calling that negative 2, I'm just going to call that 8 with a borrow of 1. It's technically a borrow of 10, but we'll call it a borrow of 1 from the next digit. So what's happening here is if you ask a young person, okay, like an elementary school first grader, and ask, you only got 5 candies. I want 7 candies out of your 5. It doesn't make sense, right? But then, the next kid has a whole bunch of candies. Then you can tell the first kid and go like, okay, I understand that you do not have enough candies, but you can borrow. But every time you borrow, you're going to have to borrow in quantities of 10, like a whole pack of candies. So this kid, who only has 5 candies, will now ask the next kid to go like, can I borrow a pack of candies from you? Where one pack has 10 candies. So after the borrow, the first kid now has 15 candies, of which I will get 7. And the first kid will now have 8 candies left. But the first kid still owes the second kid one entire pack of candies, which is going to be represented as a borrow in this case. All right, so that's the general idea. So knowing that, we can now work out all the rows in this case. So 5 minus 7 has a single digit difference in this case of 8. 1 minus 1 has a single digit difference of 0. 2 minus 4 once again has a single digit difference of 8 again. Okay? So the single digit difference is basically analogous to the single digit sum, which is basically saying, okay, we can use borrow in this case to take care of the situation. So how many candies do I have left if I have originally have 5 and someone is to remove 7 from that? So now we have to work on the borrows. So the first borrow is 0 because we are not stacking anything yet. So when we look at this borrow, or the borrow here with digit 1, now it has a 1, okay? Because 5 minus 7 requires a borrow. So I am going to switch to red here to indicate what subtraction is contributing to a borrow of 1 in this case. So now we need to figure out the borrow of digit 2, which is right here. So we look at 1 minus 1. That's okay. We don't have a borrow from 1 minus 1, but we do have a borrow from 0 minus 1. In other words, if I look at this 0 minus 1, it is contributing a borrow over here. So we still have a borrow here. And then we look at the borrow of digit 3, which is supposed to go right here. So do we have a borrow? We do, because the 2 minus 4 ends up with a borrow. So once again, we have this portion here contributing a borrow to this particular digit. So we put a 1 here. So now we need to figure out the actual difference. So the difference is, once again, just the single digit difference between the Q and the T row. Let me name the rows first. The first row is still X, the second row is still Y, the third row is still Q, and then the fourth row is T, and then the last row, the bottom row, is D. So that's just how I name these rows. So instead of K, we have T, instead of S, we have D, but the first 3 rows have exactly the same name as before. So the D row is still the single digit difference between the Q and the T rows. So now we look at 8 minus 0, which is 8. 0 minus 1 is a 9. 8 minus 1 is a 7. So the final result is 798 with a borrow of 1,000. Because this borrow here with digit 3, because this is in base 10, right? In base 10, a 1 in digit 3 is representing 1,000. So we have 798, but we owe 1,000. So when you look at the actual quote-unquote net worth, it is the correct result. Is that okay so far? More or less? We're good? All right. So this is the structure of multi-digit subtraction. So now we want to find out, generally speaking, how do we compute the single digit difference? So for that discussion, we can go back to Joplin, and you guys can focus on the right-hand side. So let me show you this. You can look at how R, which is the single digit difference, and B, which is the borrow, for the time being, when I have a cough drop, because my throat is a little dry. All right. So when you look at R of ij, which is the single digit difference of subtracting j from I, It is 10 plus I, the whole thing, minus j. The reason why I need to add 10 to I first is because it is possible that I is less than j. So I'm just going like, without even knowing whether I is in fact less than j or not, I'm just going to add 10 to it, just to make sure that it is not. So 10 minus, 10 plus I cannot be less than j, because j is a single digit, which means in this case, in base 10, it can only go from 0 to 9. So as a result, 10 plus whatever I has to be is going to be at least 9, so we won't end up with an actual borrow. Now somebody's going to say, but Tech, you can also end up being wrong the other way, which means I is a 1, j is a 0, so I end up with 11, which is not a single digit in base 10. But that problem is easy to fix using mod, because 11 mod 10 is just 1, so I get the single digit back. So that's one way to do this. If you want to use a ternary expression, there's another way to do this without using mod, which is a somewhat expensive operation. So do we have any questions about single digit difference, or the R function in this case?
It's similar to the one that we use in addition.
Not quite the same, not in base 10. But the reason why I still call it R is because in base 2, it is exactly the same. But in base 10, it's not the same.
So it's like base 2, are we, because obviously in base 2, you change the 10 to the 2, but in this case, would you also change it to the mod? Like, it's
Nope.
like 2 plus I? Or keep it 10 plus I?
Well, the first version, yes, but not the second version.
Not the second version?
Yeah. Oh, okay, so the other way to do this without using mod, let me show you what it's going to look like, is to actually to see if I is less than j. If I is less than j, then we pre-borrow the 10 first and then subtract the j from it. Otherwise, I is at least as big as j, so we just perform the subtraction by itself. So we can do it that way too. It's just, it's actually faster. The other way, using the ternary operator, is actually faster on some architecture because it doesn't involve a mod operation, which is a division operation. That's always going to be a little expensive on inexpensive architectures. All right. So do we have any additional questions about the R function, which is only here to get the single-digit difference when we subtract j from I, j and I being single-digit also in base 10? No questions? Okay. I mean, one way to understand how this works is to plug in some numbers, right? So the R of, let's say, 2 and 5, okay? So let's say I is 2 and j is 5. 10 plus 2 is 12. 12 minus 5 is 7. 7 mod 10 is still 7. So the question is, in base 10, is 2 minus 5, we're talking about the single digit difference, is that actually 7? 2 minus 5 is
-3.
-3, but if you add 10 to it, you get 7. So 7 is the single digit difference.
Oh, I see. Yeah. I see what you're saying.
So anytime you guys have any questions about the equation or it looks too abstract, you plug values into it. You plug concrete values into these to get a better understanding of how it works. So the borrow function is basically indicating if I subtract j as a single digit from I, which is also a single digit in base 10 in this case, do I end up with a borrow? Well, this one is easy because all I need to know is whether I is less than j. Because if I is less than j, then yes, I do need to borrow 1 from the next digit. Otherwise, we have a 0 because we don't need to borrow. So are there any questions about the borrow function? So that's all good? All right. So with R and B defined, we can now say Q of I is just R, or the single digit difference, of subtracting Y of I from X of I. That's kind of what we did in the example. And then d of I is also easy because it is the single digit difference of subtracting t of I, which is the borrow bit, from q of I, which is the single digit difference of subtracting y of I from x of I. The difficult one is t of I plus 1. In other words, we have two ways to generate a borrow. When we subtract y of I from x of I, that can potentially end up with a borrow, but when we subtract k of I from q of I, that can also end up with a borrow. Did we see both of these cases? The answer is yes. We actually saw both of these cases in the earlier example. Let me show you that right now. So you can see how 5 minus 7 ends up with a borrow, which is the 1 over here. But then when we subtract 1 from 0, when we have q minus t, we also end up with a borrow, which ends up to be this 1 over here. Okay? Now, there's another question. The other question is, can we end up with both borrows being 1s? So let me go back to Joplin and present. Can b of xi, yi be a 1 and b of qi, ki also be a 1? Because if that is possible, I can no longer use an OR here. I have to use an arithmetic addition here. So what do you think?
I don't think so.
You don't think so? But why?
Because
can we prove it?
It was similar to why we couldn't with the addition.
Mm-hmm.
Because there is no K. Okay. So to have the first one be a carry, the maximum number you can have is one being 9 and the other one being 9. Or excuse me, it's all flipped upside down. It's one being. Is it one being 9 and then, or the top being 1 and then the bottom being 9, right? That's the greatest. The greatest.
Yep.
Number that you possibly have, right?
Yep.
So it locks x into being 1 and it locks 9 into being y being a 9. And then.
So you're looking at what q can possibly be, right?
It's,
so okay,
it's
that's
hard to explain it, but I know why.
Yeah, I think you got the right line of reasoning, because when we know that b of xi, yi is a 1, the first thing we know is xi is less than yi, because that's based on the definition of b itself, right? It returns a 1 if and only if xi is less than yi.
Right.
So now the question is, can we look at xi being less than yi, and in addition, each one is a base 10 digit? Can we look at q of I and understand the range of q of I, right?
Right.
So now you look at xi being less than yi. So how big of a difference can they make? In other words, what is the largest q of I that can end up in this case? So the largest q that we can end up here is when xi is just 1 less than yi. Think about it, right? If xi is a 4, yi is a 5, the single digit difference between the 4 and the 5 is 9. Yep. So now we say, without any actual proof here, and we can now say q of I. Oh, wait, but what is the smallest number in this case? If I already know xi is less than yi, yep. Yep. That would be 2. Yep, that's right. So this locks down, 2 is the smallest that q of I can be, but q of I also has to be less than 9 at the same time. That locks down the range. So we can see that q of I cannot be 0, it cannot be 1 either. Is that okay? So
talk about the range of t, correct?
Exactly. So if t of I is binary, in other words, t of I can be a 0 or 1, then q as b of qi ti has to be a 0. Because the b of qi ti is a 1 if and only if qi is less than ti. But t of I can only be as big as a 1, and q of I has to be at least 2. So 2 minus 1 does not generate a borrow. So now, this is one way, but we also have to show the other way as well. So if B of this, in this case, QITI is a 1, then what do we know? What can we infer from B of QITI being a 1? This one is actually easier because we already kind of make the assumption that T of I can only be 0 or 1, right? So what can possibly generate a borrow in this case? Q of I has to be less than T of I. Can any okay, I take it back. Can any non-negative value be less than 0? The answer is no. So that means, T of I has to be a 1 in this case. Okay? But what else do we also know? If T of I is, I said 1, but I wrote down 0. Sorry about that. T of I has to be a 1.
Oh, it's because now Q of I
Has to
can't
be?
even be, well, it has to be 0. But
Exactly.
it can't be 0.
It has to be 0. Okay, so Q of I has to be 0. All right? And that in return, in what does it imply? What is Q of I again? Q of I is R of xi yi, which is the single digit difference between xi and yi. So when the single digit difference between two digits turns out to be 0, what is it telling you about xi yi? They have to be the same. Very good. Okay, so this implies t. Not t. It implies xi equals to yi, which also then implies b of xi yi has to be a 0, because in order for b of xi yi to be a 1, xi has to be less than yi. Since we already know, in this case, xi equals to yi, the b, or the borrow, of xi minus yi has to be a 0. Is that okay? So, what is this telling us? Why is this even important? Because if b of xi yi is a 1, then we know for sure that b of qiti has to be a 0. If b of qiti is a 1, then we know b of xi yi has to be a 0. So that means at the most, one of them can be a 1. They cannot both be 1s. Are we good so far? So we get back to the same situation that we had with carrying, which means, hey, that addition is not needed because we do not end up with a situation where both are 1s. We only have up to one of these two being a 1, so we can use an OR. So that is why in Joplin, I specify here with just a regular OR, which is a logical operation. So are we good so far? This is all in base 10, by the way. This is all in base 10. We are not done. We haven't moved on to base 2 yet. But what makes the R and the B specific to base 10 in this case? There's only one 10 here. Well, or if you use the other way, there's also a 10 here, which means, the borrow function doesn't even bother with the base, because as long as digit I is less than digit j, we have a borrow. Okay, it's regardless of the base. So how do we convert R and B to handle base 2 numbers? Change
The base.
Change 10 to 2. Very good. Okay, so we change 10 to 2, which in this case would be referring to this only 10 here, or these two 10s, or if you use the second definition, there's another 10 here. But nonetheless, we are just looking at changing the 10 to a 2, changing the 10 to a 2. So if you do that, okay, we end up with this particular table here. So let me just kind of do the check mark thing. This is what I can do in Joplin, which is kind of cool because you can kind of check off items that are already discussed. So the way to change the base 2 is easy. We just have to change the R of ij. Instead of using the constants of 10, we change it to use the constants of 2. So now I'm going to claim, and you can verify, in base 2, R of 0, 0 is 0. That kind of makes sense, right? Regardless of the base, if you take away nothing from nothing, what do you end up with? Nothing. Okay, that's an easy one.
Who's talking about that?
Yeah. And then do we need to borrow? If you take away nothing from nothing, Okay, that kind of makes sense, right? And then we'll skip this one and go to this one here. You got one thing, you take away nothing. How much do you have left? That one thing, right? Okay, that makes sense. And if you have one thing, I take away nothing, do you need to borrow? Nope. So that makes sense, right? It doesn't even matter what base we are dealing with here. And the last one still makes sense, easily intuitive, because if you have one thing, I take away one thing, you get nothing left, right? So the single digit difference of 1 minus 1 is 0. And then the borrow is also 0, because if you have one thing, I take that one thing away, you don't need to borrow. So the only one case that is a little bit trickier is the second one, which is you have nothing, I take away one thing. So now you need to borrow. But when you're borrowing from the next digit, which is 2, not 10 anymore. So every time you borrow, you're borrowing 2. So 2 minus 1 is indeed a 1, and that's the English explanation of why r of 0, 1 is 1 in base 2. But if that is like, okay, that's too vague, I don't like that explanation, don't use that explanation. Go back to here and then change the tens to 2's and figure out what is r of 0, 1. So if you change all of these tens to 2's and then you have I being 0 and j being 1, what do we have? We have 2 plus 0, which is 2. 2 minus 1 is 1. 1 mod 2 is 1. It works out, right? And then the b function is easy because the b of something doesn't even depend on the base. 0 is less than 1 is true, and therefore we return a 1. So now we have accounted for all 4 of the cases. So when you look at the truth table, once we have this worked out, so let me go back to Zerno here because I want to work out the truth table. So we have I, oops, okay, wrong color. You guys cannot see it. Okay, so we got I, we got J, and then we have R of IJ, and then we have B of IJ. 0, 0, 0, 1, 1, 0, and 1, 1. And based on what we observed earlier, R of 0, 0 is 0, R of 0, 1 is 1, R of 1, 0 is 1, R of 1, 1 is 0. B of 0, 0 is 0, B of 0, 1 is 1, B of 1, 0 is 0, and then B of 1, 1 is also a 0. Are we still doing okay so far? Because all I did was to summarize what we saw in Joplin, basically what we saw here, and I just turned it into a truth table. All right, so, but when we look at this truth table, do you recognize something?
It looks like 4.
Well, let's look at R of IJ first. Do you recognize R of IJ from an earlier discussion? And what would that be? It looks the same as R of IJ from binary addition. That is why I did not change the name of the function. We'll just call it R again. Okay, so that means we can just go ahead and use the old way of computing R. We can use the long way, which is using the 2 plus I, the whole thing, minus j, and then mod with 2 again. Or we can just say it is exclusive OR, which is also in the longer way or more complicated way. It is not I and j, or I and not j. Yeah, somebody complained in my previous class, having the exclamation point and I together makes it kind of hard to read. Yes, I do have to agree, but I don't think it's too big of a deal. Okay, so R is easy. What about B? Well, B is a little bit harder, but not that much harder. Because we can see that there's only one row where B of IJ is a 1, and that is when I is false and J is true. So one quick and easy way to make an expression, just to make that one single row to be true, is to say, yeah, we'll just take the one that is false and negate it. End with whatever is true on that row. So not I and J is gonna do the trick. I mean, if you're not convinced, what you can do is to look at B of ij defined like this and plugging into the truth table and make sure that not I and j ends up with 0, 1, 0, 0 for these four rows. That is the beauty of a truth table. It's easy to prove. Okay. So in fact, I'm going to do it for you right there. Okay. Now, since this is an AND, if j is false, the whole thing has to be false. Okay, so that's easy. This has to be false. This one also has to be false because j is false in both of these rows. So for the second row, j is true, which means we cannot just look at j and determine the entire conjunction is false. We also have to look at not I. But I is false in this case, not false is true, so we end up with true and true, which means there's a true here. And then we look at the last row. In this case, j is true again, and so we have to look at the other side of the conjunction, which is the negation of I. I is true this time. Not true is false, so we end up with false and true, which means the entire conjunction is a false over here. So now we can see how B of ij and not I and j basically gave us exactly the same value for the different combinations of I and j. Are we good so far? So this exercise is kind of the same thing that we did with addition. The only difference is, this time we have a B function. And that's about it. Right? So now if I go back to the notes, and I have no idea which module is which module because we got too many. Nope, that is not it. It's one of these two. Subtraction, there we go. All right, so what we have now is everything that we have talked about. So now we look at T of I, which depends on T of I. So once again, we have a ripple effect thing because in order to compute T of I plus 1, we need to first compute T of I. In order to know T of I, we need to know T of I minus 1. In order to know T of I minus 1, we need to know T of I minus 2, and so on. So we still have this problem of, so the amount of time it takes for this subtractor to work is proportional to the number of bits, which is something that we don't like. That is the whole reason why we have carry lookahead for adding. So the question is, can we do something like this for subtraction? So now we have a bunch of Boolean algebra kind of derivation. And I'm not going to name all of these derivations. They are basically the same thing as when we walked over the binary addition, Boolean algebra derivation, with only two differences. This one also had to use De Morgan's law. So De Morgan's law was used early on. This is one application of De Morgan's law, and then this is the other application of De Morgan's law. Do you need to know De Morgan's law? Well, probably not in this class. Okay. If you take CISP310, De Morgan's law should be introduced in that class. But I do want to kind of give you an idea of what is De Morgan's law now that I have mentioned it, because some of you may be asking this in your mind. What is De Morgan's law? So what De Morgan's law is saying is if you have the negation of, okay, let's not use I and j. I'm going to use xy, which has nothing to do with the xy as the rows. I'm just using those two as names of variables. So if you have the negation of x, and this time I'm going to use explicit n here. Oh, you're right. I forgot. There we go. So if we have the negation of an and, which is NAND, this turns out to be the same as negating the x first, and then or the negation of y. That is one version of De Morgan's law, but it works the other way around as well, which is you have the negation of x or y, and that turns out to be exactly the same thing as the negation of x, and this time with the negation of y. So both of these are basically parts of De Morgan's law. And turn out this is a very useful rule in Boolean algebra. This is also partially how I can derive the negation, how I can express OR using NAND. Remember that kind of long-ish equation? That's actually the application of De Morgan's law. So one way you can look at De Morgan's law is a weird way of distributing a negation into the components of a conjunction, or distributing the negation to the components of a disjunction. But as you do that, you have to change the and to an or you have to change the or to an and. So depending on which one you start off with, the end result would be the other one. So you look at this and go like, well, that looks kind of awkward, looks kind of weird. Are we really sure this works? Well, I'm glad you asked, because what you can do is, once again, how do you show that the first one works or the second one? What trick do we use?
Do we just plug in values?
Okay, but we want to do it in a very systematic way. There's a name for that kind of structure. How do we call those structures? Exactly. So you can use truth tables, this time 2 truth tables, one for the first version of De Morgan's law, and then the second one for the second version of De Morgan's law. Then you can prove it to yourself that the equivalency actually does work out. And this turns out to be really useful for computer engineers. All right, are we good so far? Okay. And now we are getting back to this thing here. So what you can do is just to focus on T of I plus 1 can be expressed as not xi and yi, the whole thing, or not xi or yi, the whole thing, and T of I. Okay, the intermediate derivation is not really that important. So you go like, but heck, we're still not solving that problem, because T of I plus 1 still depends on T of I after all this work. You'll be right. But then we define G of I and P of I, but this time differently. So G of I is now defined to be the negated X of I and Y of I. P of I is now defined to be the negated X of I or Y of I. So they look very similar to the way we define P and G for binary addition, except in this case, we negate X first. That's the only difference. Are we good so far? So after that, we end up with this template here. So this template says T of I plus 1 is G of I or P of I, T of I. So when you look at this, and then you look at the binary addition slide, that's coming from my Discord. Should probably turn it off. But anyway, getting back to here, look at this template here. This template, in fact, I'm going to do that trick so it's easier to focus on that template. So I would take a screenshot of this and make it always on top. And then switch back to the subtraction module. There we go. And now we look at these two side by side. Do you recognize the structure? The only difference is on one side we call it K, and then on the other side we call it T. Does that mean the same trick is going to work if we just do the expansion and the substitution and all that stuff? Yes. So without using the expansion, without showing you the expansion here, I'm just going to say, well, in the end, we got the same thing as last time. You go like, well, heck, does that mean that we can use the carry lookahead adder, just negate the X before we make the G and the P, and turn it into a subtractor? The answer is yes. A borrow lookahead subtractor is structurally identical to a carry lookahead adder. The only difference is whether we are negating X first or not, when we compute P and G. That's the only difference. Okay? So in terms of the circuit, what are we going to do with that? Okay, this is like perfect timing because this is exactly the time that I would like to end this lecture. But before we end it, I'm going to show you the circuit that we were working on earlier today. We are so close to the end. This is in. There we go. Oh, try that one more time. That. Come on. I wanted to maximize on this side. All right. All right, that should work. There we go. All right. So what do I mean, when I said, the P and Gs are computed differently? This is how we compute the G. This is how we computed the P. So that means this is all we need to do. Go here and say negate the first input. So negate the top, turn it into a yes. Go to this guy, do the same thing, negate the top input. Now we have a subtractor. With the same circuit, K1, K2, K3 become misnomer because in this case, because of the way I redefine P and G, K1 should have been T1, K2 should have been T2, and then K3 should have been T3. That is how we turn a adder into a subtractor. It really is just as simple as whether to negate X or not when we compute P and G. All right, so we are out of time in the lecture, and I forgot to take roll, so I'm going to do it now. Let's see, go back to this here. I said about time already, but I think I might need to give you guys a little bit more time because you won't have enough time if I maintain that one. So we'll make it noon. So there we go. And I have to show you the answer to the question as well. Let me just get rid of Discord right now. Those are all Design Hub traffic. All right, so the word is loan. And can anyone guess why I chose the word loan in this case? Yeah, exactly. All right, so you should be able to see it now. It is 20220912 as the name of the road taking activity. And then the word is loan, L-O-A-N. All right, so let me go ahead and release the lab for today. So the lab of today is the continuation of the lab on the other day. I can turn off the streaming now. So. Uh-oh. That is not good. All right, so let me turn this on first, and then we'll fix the other one. So this is going to be due, so the access code is 3x3b. That's the access code for the lab. And it is due today at 1:20. This one is easier, by the way. And you can use my circuit as the starting point as well. So that should make it a little bit more reasonable. And it has a companion quote unquote assignment to collect the file. So here's the file collection. And let me change the due date here to also be 1:20 p.m. There we go. All right, so you got the labs. And OBS is not responsive